Swayam Prabha. Digital India. Educated India.
Good morning everybody, and let us go through some more information about our courses on introduction to micromechanical machining. So, in the last class we have seen 4 different mechanism by which you can remove the material, and that is in terms of the uncut chip thickness ratio to the cutting edge radius. So, we have seen this particular location of the point S here, and in the form of what is the angle of a rake angle. So, mostly we know that in the when you do machining at a micro scale, you are mostly end up with the negative rake angle, and because of the negative rake angle, the formation of the chip becomes little bit difficult. In the last class we have seen 4 mechanism. One was the shearing mechanism. That shearing is important because this is what we need to form a chip in this case, and then gradually we move this particular point from this location to this location, then moving to this location, and then this location. So, we have seen the different mechanism. So, one was the shearing mechanism, then it was a extrusion, then it was a ploughing, and then finally it was the rubbing operation. So, what is important? So, this shearing is important. These 2 things should be completely avoided, and in this particular extrusion case also you may get a small amount of chips and some of the material will be extruded through the workpiece. So, this should be also avoided. So, our objective is to do machining at a shearing operation, shearing form or shearing mechanism, but not through the extrusion, ploughing or the rubbing operation. So, let us continue further. Right. So, fine, last class we have completed rubbing portion, and we understood and concluded that the rubbing deteriorates the surface quality significantly. So, we have to avoid the rubbing operation. Now, let us see what is the size of the influence in size effect influence of the size effect on the different parameters. Now, this particular diagram tells us many things, that when you do machining at a HC by Rn, that is this is your HC and this is your Rn. So, when you do this thing, so HC is equal to Rn or it is a little bit smaller than Rn. So, we are not talking about a very large negative rake angle. So, what is happening in this particular case, that your whole material is separated into 2 flow. So, this is the one flow, it is showing in this direction, and another flow is showing in this direction. So, this is called the material flow separation. Right. So, one goes over the rake face as a chip, this particular thing, and the other is compressed under the tool flank surface. So, this is the flank surface of the tool. So, let us see, this thing is a rake surface, and this one is a flank surface. Correct. So, this is what is happening in this case. So, material above the separation point D. So, this is the point we have discussed in last class, all the things that we have found, that this D is moving from here to this downward, so that you are getting a different mechanism of material removal, or sometimes the material deformation mechanism, not actually the removal mechanism, because in many cases material was not removed in terms of chips. So, here the material above the separation point D moves parallel to the rake face and is subjected to tensile stress. So, this whatever material is coming out, this will be in the tensile stress, because we know that whatever is material uncut chip thickness, that the thickness of uncut chip is smaller than the thickness of chip. So, whatever chip it is coming out of there, this will be bigger than the uncut chip thing, because this chip will be little bit expanded when it is cutting out at that. Everything depends on the what is the size of the or length of your shearing angle. So, now see the whatever is the shearing angle, this particular length you consider x and this one you consider y. So, your x is larger than y. So, in this case it will be mostly in a tensile stresses, and you are getting a chip out of this particular mechanism. Now, coming to the minimum chip thickness. Now, we have seen here that in many cases what is happening, that you are not able to remove material. So, there are two parameters, one was the rake angle, that is mostly going into the negative side, and another one is the chip thickness, and we are constantly comparing these two parameters in the last many cases. So, what this the minimum chip thickness, the determination of the ratio of minimum chip thickness to the cutting edge radius is essential in order to avoid or minimize flowing effect and achieve the desired material removal. So, let us see the first figure here. Now, what this figure tells us, that now this one is the minimum chip thickness required, that this is the minimum required to get the material in terms of chip. So, this is called the minimum chip thickness. Correct, and this is what we have set right now. Set H in the machining, correct. So, now right now you consider H is smaller than the HM. So, what is happening right now, we are keeping RE constant, that is the cutting edge radius is constant. Right. So, cutting edge radius is constant. So, we are continuously changing this edge. So, ultimately if you change one of these parameter of RE or H, you are getting different ratio of the uncut chip thickness, right. So, first thing let us see that your setting H, whatever you have given depth of cut, that is smaller than the uncut minimum uncut chip thickness. So, what is happening in this case, your RE is very large in this case, R is very large than the M, not HM, but only M, H. So, this is what is happening. So, in this case we know that negative rake angle is very large again, and because of that what is happening here, this one is called the rubbing operation, that it is elastic recovery. So, it is also different than rubbing operation, because recovery means that you are just moving this particular tool over the surface, and once this particular tool is passed, your surface again resurface on this, that your surface is again recovered. So, whatever is this particular edge, if you consider this particular line or consider this is the end of the surface. So, this whatever is this total thickness, it is d. So, same thickness will remain here in this case this. So, in earlier we have seen some of the operation where the material was deformed, but deformed material became a part of the machined surface, right, but here there is no machined surface. So, whatever we are doing here, we are working within the elastic range of the material. So, within the elastic range, what is going to happen, that if you remove the load, then material come into the original shape. So, this is what is happening in this particular case. Your tool thickness or the uncut chip minimum cut chip thickness is so low that your material is not crossing this elastic limit of the material, and that is the reason that as soon as tool is passes through this workpiece at a edge, at that time your material will be resurfaced here at this location, it can recover and again thin the part. So, this is completely not acceptable in the machining part, because what is our objective? To remove the material. Now, this is the second case. Now, here what is the difference here? The difference is only one thing, that your H is similar to HM. So, now we have little bit increase our H. Now, if you see H here, this H is little bit larger than the HM. Still RE is constant here in this case, we are not changing RE in the different cases. So, now once this is the H, now what is happening, that now your tool is little bit penetrated inside and it has crossed the limit of the elastic recovery. But here still it is within this particular zone. So, what is happening, that some of the material will escape as a chip, but still some of the material which will be recovered as a elastic deformation, but still you will get some material removed. Now, see your H is this much, but you are getting material removed this much only, and remaining part will be consumed as a elastic recovery of this particular part. So, what is the problem of this particular? This is completely unacceptable. By chance you are getting here, but your chip is not required as our H, then some of the material will be recovered. So, now in the next round of this particular machining, what is happening? Now, see suppose this is your workpiece, this is the chuck and this is the material. Now, you are removing the material, considering that you needed 2 pass to reduce this particular diameter, and now this is the 2 pass, this is the first pass. Now, considering the first pass you have removed this material, right. So, whatever depth of cut you are giving here, suppose depth of cut is we have given that 200 micron, 200 micron depth of cut. Now, out of 200 micron, now consider that 150 micron is going as a chip, because that is what is showing here, some part will be going as a chip, and 50 micron is a elastic recovery. Okay. So, now what is happening, that now you have 2 constant depth of cut, that 2 cycle of 200 micron of depth of cut. So, in the first cycle we have given this command, and unfortunately this 50 micron is still available there, only 150 micron is removed, but we do not know during the machining that this has happened. Now, first cycle is over, you are going for the second cycle. So, theoretically your second cycle or second not cycle, let us put a pass, that is more appropriate word. In the second pass, how much material we want to remove? We want to remove 200 micron, or that is the 200 micron depth of cut. But what is happening actually, that you are giving depth of cut of a 250 micron. because 50 micron is already recovered here. So, now we know that we have set this particular speed, feed and depth of cut parameter depending on the geometry of the cutting tool, the type of the cutting tool and the workpiece material properties, many things. Now, we know that 200 is giving the optimum result out of it, but now because of this particular phenomena what we have encountered that we are removing material as a 250 micron depth of cut. So, now our set parameters are not effective here because it has overcome that one particular parameter, that is depth of cut is actually changed here. So, because of that reason what happened that you are not working or you are not operating your machine as a optimum parameter, and that is the reason that you may encounter the breakage of the tool, very high tool wear or the different properties on the workpiece machine surface, and that is the reason because of this mixture of the elastic recovery and the removal of the material. So, that is what is happening in this particular case. Here what is happening that you are not removing material at all. So, nothing is going to happen to the workpiece. Some of the material you are removing in this case, but some of the material is again resurfaced or the recovered on the part, and that is the reason that you may encounter the different failure of the tool, because every time you pass or more number of pass you from here and everywhere, every time you are end up with the more amount of depth of cut than the set depth of cut, and that the reason for degradation of the property of the workpiece also and the degradation or the breakage of the tool also. So, now let us see what we have to do to get this thing correct. So, now this is the third case. What is happening in this third case, that your set H value it is higher than the minimum uncut chip thickness. So, now this is the set value. Now, if you see this R value and this H value is slightly higher than the RE value. So, now what is happening here, now your tool is already penetrated in such a high that you are not going to get a elastic recovery of the material, and whatever is this thing here you will get the chip out of this particular part. And this is the what is important thing here, that we have to maintain a minimum uncut chip thickness in such a way that you are always getting the chip from the uncut chip or the minimum cut chip thickness, minimum uncut chip thickness, so that no material is getting the inside the workpiece material or no any type of recovery from the machine zone. So, this is the required condition to get the material removal in terms of chip. Now, what are the failure in the ductile material? Now, see, we know that no material is perfect completely. There are maybe different type of defects are available, and because of that defect you are always get a one type of initiation or the some type of propagation of the cracks or propagation of the deformation surface. Now, we know that this is one of the schematic diagram of the grain structure of this part. So, now you know that there are grain boundaries available. So, these are the grain boundaries, these are all the grain boundaries. Now, intrinsic defects are available, there are pores available, these white portions are the pores, and there are some impurities also available. Impurities means some of the foreign element is available here, that means it may be harder than this base material or it is softer than the base material also there. So, these are the some of the defects inside it. So, now see what is happening when you have some type of defects in the material and you are actually deforming this material in the both the direction. This is in the x direction, let us consider, and this is in the y direction also. Now, first thing is the inclusion. So, these are the inclusions. So, what are this? This inclusion means there are some defects, right. So, whatever these defects are there, those defects are the inclusions. So, these are the inclusions, right. So, whatever these things are showing here, these are the inclusions. Now, you are actually putting this workpiece in the tension in both the directions. So, this inclusion will behave or it will be origin of the breakage or the origin of the void, and then that void will continue to propagate, and finally, you are getting a breakage, right. So, second after inclusion, what is the new void nucleation. So, once these particular inclusions are available within the material, what is happening that when you are actually putting this workpiece in tension in both the direction, this particular void will be original of the deformation of this particular workpiece. So, it is failure is created from this location. So, wherever it is a high load, your workpiece will be elongated in this direction. So, this is whatever this white portion is available. So, this is the extra amount of failure. So, now your workpiece is getting elongated in this direction, right. So, now if you continue this thing, this void will be grow, and this growth of this void will create a one particular direction where the distance between the voids are very less. So, now if you see this particular thing, then you are end up with this particular 5 thing. So, these 5 are such a way that the distance between these two are very less. Now, this is also little bit far away from that, and this distance are very small in this case. So, now the next step is the strain localized between the voids. So, now the strain is getting localized between this, because now distance are very small, and it is very easy to merge this particular void growth. So, now this is the black color part is showing the localizing between the voids, and then the necking between the voids. So, now necking started in this particular location, and then finally whatever the void coalesces and the fracture happens. So, now your part will be broken from this particular direction. So, this will be the first upper part and this will be the lower part. So, now what is the meaning or what is the objective of showing this particular slide is that every material has a defect, and that defect will be a nucleation of the deformation or the cutting of the material. So, higher the level of this defect, more easy will be the material removal. So, higher the level of defects, more easy to remove material. But that is not the case that you have to select the material with a higher defect, but our objective is to reduce the level of defect in a initial stage also, because this is what we are telling, that material has some defect, but that does not mean that it should be have higher defect. Our objective is to find out that at which particular defect level material is acceptable for the final application, and whatever defects are available within that material, how many defects are there that will originate or that will nucleate the deformation or the fracture of the particular workpiece material or the failure of the material. So, this thing will decide that how much is the energy required to remove the material, but that does not mean the defect should be present. We need a defect free material, but no material is defect free. There are some these type of things are available, and because of that you are getting the material removal at a different mechanisms. Right. So, during the machining at when you are talking about where this HC and this material adjustment tool is separated into 2 flows, that we have seen in the last class. So, what is going to happen with this particular thing? Material contains defects. So, whatever defect we have seen, the grain boundaries are also considered as a one of the origin through which the material is separated out. Missing and impurity atoms are also available in this particular case. Now, see, these are the defect levels. So, we have seen that in earlier slide that many things are created or nucleated because of the presence of these particular defects. So, plastic deformation in materials usually starts in area where the defects are present. So, now suppose this is the particular condition. Now, if you see this particular, this is the point of the contact between the tool and the workpiece material. If you continue in this direction, you are not encountering any defects till now, and then suddenly you are getting 1 defect, 2 defect, 3 defects, depending on this particular property of the defect, whether the defect is inclusion or porosity or something other than that. Depending on that, the forces or the load on the tool will be fluctuated, and when you are passing through this thing, you are getting a different magnitude of the force is on the tool, and that will decide the tool life and the efficiency of the machining operation. Right. The material resists plastic deformation much more strongly than expected due to less defects. Now, this is you consider the normal machining operation, that means you are considering the macro machining or conventional machining, where your depth of cut is very larger than the uncut chip thickness. That because right now we are showing the sharp cutting tool. So, that means we are neglecting the uncut chip cutting edge radius in this location, and now this particular thing whatever is showing here, it contains many grains, many layers of grains. So, these all things are the consider the grains layer, and now within that particular things that you are, there is a high chance that you are end up with the grain boundary, and material removal is very easy to pass through these particular grain boundaries. But now if you see that you reduce this particular scale of the machining part, and then what is happening here in this case, that now this is you consider this particular thing. Let me clear this part first. Now, this is the deformation zone. Suppose now this is the uncut chip thickness. Now, you are reducing from here to here, and then you are reducing from here to here. Now, you can see that within this particular area your number of defects were very large, and if you reduce your machining area or uncut chip thickness, the number of defects which will be encountered by the cutting tool will be little bit less. So, now what is that mean? That now we know the material resists plastically deformation much more strongly than expected due to less defects. Now, we reduce the scale, your defect level is very less, that means voids, cracks, whatever is there, that is in small volume. If defects are less, what will happen? Material will behave strongly. So, you have to apply more amount of force here for cutting of this material. So, now this is the problem in this particular case, and that is the reason that what we are doing right now, that when you cut the material at this level, you have to find some of these particular things by which your material removal will be very easy. But that is not going to happen, because yes, you are going down and down in the material removal, at that time the defect levels are very small, and because of that, that is the what is happening in this particular case. Here your material removal will become very difficult. Other than that, right now we are considering our cutting tool is a sharp, but we have seen that our cutting tool has also one finite cutting edge radius, and many times we have seen that your cutting edge angle is very rounded, and because of that your tool is also not sharp, you are not getting the number of defects also very large. So, both these things are combined, and that will make the material removal very difficult. So, let me finish this lecture here, and we will continue from the next class about more detailing on the micro machining operations. Thank you very much.